So hello, and welcome to our final Tux Sanders Series guest lecture of the 2015-2016 academic year. So to close the distinguished speaker portion of this series for this year, I'm very excited to introduce Dr. Yang Li from Google Research, who will be talking about enabling new input dimensions for mobile interaction. Dr. Li is a senior research scientist at Google and also an affiliate faculty member in computer science and engineering at the University of Washington. Following undergraduate and master's studies in computer science at the Northwest University of China, Dr. Li earned his PhD in computer science from the Chinese Academy of Sciences, with research focusing on pen-based user interfaces. He then continued on to do postdoctoral research in electrical engineering and computer science at the University of California, Berkeley. Dr. Li's research is in the area of human-computer interaction, obviously, with a focus on predictive user interfaces, gesture-based interaction, and also new tools and approaches for creating mobile interaction, including emerging input modalities such as gestures, cameras, and cross-device interaction. To this end, he developed software tools and recognition methods that draw insights from user behaviors and leverage machine learning, computer vision, and crowdsourcing techniques in order to simplify complex tasks. Among his notable achievements, Dr. Li wrote Gesture Search, a popular Google-branded app on the Play Store, and also led the development of app launch prediction on Android, which is used by tens of millions of users, which is very impressive. Dr. Li is an ACM senior member and has published over 50 papers in the field of HCI, including over 29 papers at CHI, WIST, and Tokai. It's also worth noting that his upcoming paper on cross-device interaction scripting is the winner of a Best Paper Award at CHI 2016. So without further ado, please join me in welcoming Dr. Yang Li. And just one last note, if you could hold your questions until the end, we will have microphones circulating, just so that we are recording the presentation so that we could capture your question as well as the answer. Thank you.
Thanks for the nice introduction. It's a pleasure to be here. I saw a lot of exciting projects this morning. I'm looking forward to more conversations with the folks here. So today I'm going to talk about our work on enabling new input dimensions for mobile interaction. Much of this work was conducted with my interns over the past few years at Google. So it's clear now that mobile devices have become an important part of our everyday life. According to this report from Klein and Perkins, one of the top venture capital firms, users on average use their smartphones, access their smartphones about 150 times per day. These include making phone calls, messaging, and other typical activities we would do throughout the day. But the way we can interact with mobile devices is still quite narrowed. So existing mobile interfaces are largely structured based on traditional graphical interface concepts. The functionality of the system is exposed to the user through the graphical representations. The small form factor of mobile devices really constrain the amount of information we can present on display and what we can possibly acquire. So the input bandwidth is further constrained by the lack of precise input devices. For example, a target item has to be large enough for finger to acquire. So as a result, the rich functionalities of a mobile device has to be presented through a deep UI hierarchy. Navigating this hierarchy requires a significant amount of visual attention and precise motor control that are not affordable for mobile user. So fundamentally, traditional user interfaces mostly rely on the 2D coordinate of the touch point and the target being acquired. This paradigm essentially ignores the rich semantics of user actions and the behaviors that can be potentially more effective in communicating what we want to achieve. So the goal of my research is to push the boundary of what a computer system can possibly understand about our actions and behaviors to expand the input bandwidth of mobile devices. To this end, I have worked in 3 areas of research. These research directions leverage unique aspects of mobile devices, such as their sensors, usage patterns, as well as the ecosystem. Much of this work also spans both end-user-facing systems and developer tools for those who are interested in creating novel input techniques. So first, I want to talk about the gesture input. I will start with a simple project. So as I mentioned at the beginning of the talk, users tend to access their smartphones a lot. Many of these accesses actually require the user to go through this tedious process to turn on the screen, unlock the phone, then navigate the deep UI hierarchy. So this additional effort is like a heavy taxation that is imposed on every mobile access. To address this problem, we developed a system that allows the user to access their smartphones using gesture shortcuts directly from the standby mode. So say we want to start the YouTube app on the phone. Before we even turn on the screen, we can simply draw a letter Y on the screen. So the system returns a list of results where we can select the YouTube app. I'm not sure if you see the gesture. Did you see that? Okay, cool. So it all looks good that we can quickly access a functionality without having to go through all these additional steps. But as you can imagine, there are a few challenges to achieve this functionality. For this to work, the touch screen has to be always active in sensing touch input, even when the screen is off. It's quite possible that the user accidentally touches the screen, for example, when the phone sits in the pocket, or when the hand touches the bezel of the screen while holding the device. The continuous sensing of a touch screen also can have a significant impact on the battery life. And in addition, can we unlock the phone by just using the gesture the user draws without having to ask the user to go through the dedicated authentication step, such as entering the password? And finally, how can we infer the target item from the user gesture? So here, I'm only going to talk about some of the problems. First, we need to tell intended gesture input from accidental touches. To do this, we instrumented a set of Nexus 5 devices to constantly sense touch input as well as other sensors, even when the screen is off. So we asked a group of participants to use these devices as their phone over the course of a few days. On average, we observed a user generated about 800 accidental touches per day. So that's a lot, actually. So we also asked the same group of people to draw character gestures in a controlled environment, including holding the phone single-handedly or by manually when the user is walking or sitting. So based on this data, we analyzed how gesture input is different from accidental touches, as reported by multiple sensors, including the touch screen, the proximity sensor, and the accelerometer. So next, I want to give you a few examples about the analysis we did based on this data set. Both accidental touch and intended gesture input would generate a sequence of touch points, which we refer to as stroke. So the heat maps here show how touch strokes are distributed on the screen just to clarify, we use the point on the stroke that is the farthest to the bezel as the location of the stroke. As we can see here, accidental touches are on the screen almost uniformly, but the intended gestures are more concentrated at the center of the screen. So this is actually because accidental touches, they occur more randomly, but when the user draws a gesture, they tend to choose the center area of the screen for our articulation. So that was a useful feature to tell intended gesture input from accidental touches. The characteristic difference between these two types of behaviors is also well captured by other sensors, such as accelerometers. For example, the histograms here show the acceleration doesn't change much for intended gestures because users trying to keep the device stable while drawing the gesture. But this is not the case for accidental touches. So based on this analysis, we trained a simple decision tree model that combines 8 features based on 3 sensors, so the touch screen, the proximity sensor, and the accelerometer. The model achieved good accuracy in terms of precision and recall. Next, I'm going to show you how well the system works in detecting intended gesture input out of accidental touches. So as we can see here, these touches will not trigger any actions. But once the user draws a gesture, the system will respond right away. Okay, so far I have talked about how we can detect the intended gesture input from accidental touches. But once we have a gesture detected, we need to infer the target item the user wants to access. There are multiple levels of ambiguity in the process. First, the system can incorrectly recognize the user gesture, and the user can misspell the keyword of a target. And on top of this, it's often ambiguous to the system which target the user wants to access, given just a few gestures the user draws. For example, letter Y could be for Yelp as well. So these challenges were addressed by a subsystem named gesture search. It captures all these levels of ambiguities, both on the UI and in the underlying algorithms. So here I just want to briefly talk about the algorithm here. So in the underlying system, we use a single probabilistic model to encode how input gestures lead to different targets. And every time a user interacts with the tool by clicking on the search result, the system updates the probability distribution in the model. So the model is heavily personalized for the specific task of the user. So here I want to briefly talk about the large-scale log analysis we did. So in general, as we can see here, the more gestures the user used for access or the longer the query is, the more likely a target item will show at the top position in the search result list. So once we consider user behaviors with personalization, we can significantly reduce the number of gestures we actually need to bring a target item to the top position in the list. So in general, overall, personalization or prediction based on user behaviors contributed about 46% of the entire traffic. And on average, each access takes less than 2 gestures to achieve, which means a target item is often a couple of strokes away. So gesture search is available on Google Play, and it has a few other useful features. It supports more than 50 languages, and you can write a mix of them without telling the system which language you're writing. and I encourage you to try it out. So at this point, you might be wondering if we can go beyond just using character gestures. For example, how about using the plus sign for G+, and the cursive writing of NY for New York Times? To support these arbitrary symbols for gesture shortcuts, a typical approach is to assign a symbol to each of the targets in advance. Then we can match the user gesture against the predefined templates. So my colleagues and I have developed a few template-based recognition algorithms. They have been used by other researchers because they are simple to use. But the one big problem with this approach is that these templates have to be manually defined in advance. It's non-trivial for the end users to define or memorize them. So, in other words, this approach actually doesn't scale. So at this point, we then ask the question, can we actually invoke any target with arbitrary gestures without having to have the user to define them in advance? So it sounds like impossible. Before I talk about how we can have how we can create a computer system to do that, I'd like to test this with you first. For example, for this gesture symbol here, can you guess the target functionality or target app the user wants to invoke on the phone? Angry Bird, okay. Yeah, I mean, this is my favorite part in the talk, but cool. One more. Postgres. I think it's really too easy for you. Oh, you. Okay, last one. Wow, what is that? Music, yes. Okay, cool. So I tried this actually quite a few times in the past, never failed. So we can keep doing this. So the fact that you can guess the meaning of these gestures does tell us something. We humans think alike. So I will come back to this point later on. So to understand how users derive and perceive gesture shortcuts, we asked a group of participants to define gesture shortcuts for over 400 targets, including applications and websites. These gesture symbols can be entirely arbitrary and only meaningful to the user. Here are some examples from the study. So this open-ended study revealed several important findings that inspired us for handling unconstrained gesture shortcuts. So first, as we can see here, there's a mix of drawing and character-based gesture shortcuts. Character-based gestures are more dominant. This partially explains why gesture search actually works. It relies on character gestures. So we also see quite a bit of a commonality across gestures that are created by these participants independently. So in this experiment, we're trying to guess the meaning of one user's gesture based on those defined by others. The accuracy here could be even higher if we had more participants. So based on these discoveries, we designed a system that can infer the meaning of arbitrary gesture. For each unknown gesture, the system tries to recognize it. First, using a cursive handwriting recognizer that is based on a language model dynamically constructed on the user's device. So it's heavily tailored for the user's corpus. At the same time, it tries to match the gesture against those actually used by other users, the crowd. Then it combines the outcomes of these two gestures, two recognizers, to generate the final prediction list. If the target is not in the list, then the user can manually specify it in the system. But the system learns from every interaction of each user. It gets smarter and smarter over time. So collectively, there's no magic in inferring arbitrary gestures, but this works like magic to a specific user, to each individual user when the system is able to guess the meaning of an arbitrary gesture. I forgot to show you these. So this is a quick video about how the system works. As we can see here, we can draw cursive gestures. We can also draw drawing-based gestures. So the system continuously recognizes user input even before you finish a gesture. The system also exposes the gestures that have been used by other users to accelerate the convergence of this user-defined gesture shortcut language. So we then asked a different set of participants to try out the system. They can use any gestures they can think of to activate a set of given targets. As we can see here, matching with the crowd gestures and the cursive handwriting recognition played an important role at the very beginning of the experiment. And as the system sees more and more gestures from the user, matching with the user's own gestures became the most important prediction source. It's important to notice that at the beginning of the experiment, before the system sees any gestures from the user, it was able to guess user gestures 77% of the time. This significantly reduced the user effort in defining gesture shortcuts. So later on, we took this idea of cross-sourcing power recognition further by developing a general platform for creating recognition techniques. Briefly, a developer can describe a recognition task and the budget he or she wants to spend on the recognition task. Then the task is distributed to mobile workers. As the data comes in, Crowd Learner continuously trains the recognizer whenever the recognition accuracy falls below a certain threshold. So the compelling result we got here is that the developer was able to acquire a usable recognizer for shape recognition with less than $10 and under 2 hours. So far, I have been talking about touch-based gestures. Another form of gesture that is using motion is also quite interesting. I'm not going to talk about this line of work in detail. I just want to show you a quick example about what we have worked on. It's called side tap. Basically, you can tap different side of the phone to activate the corresponding functionality. So a lot of users examples that I talked about for gesture input have been related to invoking shortcuts. But actually one major use of gestures has been on direct manipulation. So it's amazing how many multi-touch gestures are enabled in mobile applications such as maps. Although these gestures are intuitive and efficient to use, they're often difficult for developers to implement for a number of reasons. To understand why it's actually difficult to implement multi-touch gestures, I first want to talk about two fundamental problems in any form of interactive computing. So one is to identify the target interface object we want to manipulate, and the other is to determine the operation intended for the object. For traditional graphical user interfaces, These can be easily achieved with a precise input device, such as a mouse, and a set of well-defined input events, such as clicks, drag and drop. But that's not the case for multi-touch interfaces. When we land our fingers on the touch screen, it's often ambiguous to the system which object we want to manipulate. For example, one of the fingers here partially falls on the canvas underneath the photo. So with multi-touch gestures, users can often express rich operations semantics such as zooming and rotation through continuous motions and complex finger transitions. Although these behaviors are natural to the user, they are actually difficult for developers to program manually. So we intend to create advanced tools for developers to create multi-touch interaction in their applications. So next, I want to give you a quick video about the system we actually developed for multi-touch interaction. So here, let's assume we want to add a set of gestures, multi-touch gestures for our application. It's called a photo album application. So this is a typical Android Eclipse setup. First, we want to add a gesture library to the project. So we bring up the gesture creation tool that's a plugin in Eclipse. Then we can directly demonstrate our target gestures on the real device, tablet here. So the system can recognize the common gestures and automatically add them to the gesture set. If all we need are these common gestures, with less than 20 seconds, we have created our gesture set. But what if we want to create a new gesture? For example, three-finger pinch. The system recognizes that as a three-finger swipe. In that case, the developer can give it a correct name, three-finger pinch, and the system learns from that. From now on, it can correctly recognize the three-finger swipe, three-finger pinch, sorry. So that's how we can add a new gesture to a project. So a gesture set has a XML specification generated where we can finely tune these gestures. For example, we can specify the temporal and spatial constraints for these gesture behaviors. And with these, we can easily enable a set of multi-touch behaviors in the photo album application, our example application. Here we can manipulate each individual photo and the entire canvas. So we can transition from one behavior to another without having to lift all the fingers. It's kind of difficult to implement if you ever program in multi-touch interaction to keep track of all the states. We can also select a group of photos as a collection, then we can manipulate the whole collection of photos as a whole. So developers can easily enable these rich behaviors in their application while the system handles all the complexity underneath. So next I want, okay, so I should just talk about studies. So we evaluated the tool with 8 professional programmers who had programmed Android applications. On average, it took them about 20 minutes to create multi-touch behaviors for a given application. But in the baseline condition where this tool was not available, none of the participants was able to finish the task in a given time frame. That was like 45 minutes. The comment was made by one of the participants when he realized how complicated it is to enable these multi-touch behaviors. So now I want to briefly talk about the mechanics under the hood. So as I mentioned earlier, there are two factors in any form of interactive computing: the target interface object and the intended operation. So here we use two random variables to capture these two quantities. And the probabilistic dependency between these two random variables indicates that the interface object determines the type of gestures that are possible. For example, a button is supposed to be clicked on, and a list can be scrolled. So we then design our inference model based on a dynamic Bayes network. It infers the current interface object and the gesture from a sequence of touch points, raw touch points. So part of the inference is based on how the observed touch events match a given object and gesture. For example, how well does a touch event fall into the boundary of an interface object, and how well does the continuous motion of touch events demonstrate a scaling transformation for pinch gesture. The other part of the model captures how the previous interaction state influence the current state. For example, a tap gesture would expect the finger to lift up after it actually goes down. So the model seems quite complete in capturing a variety of factors that determine the interaction state. So I'm going to talk a little bit about how the model is created. Basically, instead of manually creating this model, the system learns an inference model for each gesture from the demonstration or XML specification. At the end of the runtime, depending on how these gestures are allocated to the interface objects, the system dynamically instantiates and assembles these individual models to form a global inference model. So that's all I want to talk about regarding the inference here. So next, I want to talk about a different topic. There's apparently a lot to explore in creating new interaction techniques. But I want to touch on this research area I have been working on and gradually shifting my focus to. So mobile devices are essentially context-rich because we use them anywhere and anytime. By learning from user behaviors over time, it is possible that we can predict the next actions the user wants to perform. For example, people to contact, applications to launch, and places to visit. Then based on these predictions, we can optimize the interface to reduce the need of user input and to maximize and to increase interaction efficiency. So to predict next user actions, the typical techniques that has been used widely in commercial products is the recency, right? The more recent event is, the more likely it is to reoccur. Indeed, this simple heuristic is quite effective in predicting next user actions. There's more than 25% chance the most recent event will reoccur. But as soon as we want to develop more advanced prediction methods, it becomes complicated. Creating an advanced prediction method requires high levels of technical expertise, such as machine learning, that is often beyond the reach of average developers. And developing a prediction component for each app involves a lot of repetitive engineering effort, and it's also computationally inefficient. In addition, a mobile interaction is often situated in a much larger context than each individual app. But it's technically infeasible for an application to observe user behaviors across applications. So to address these problems, I took an infrastructure approach by developing an on-device service for event prediction. It exposes a simple set of APIs for developers to easily enable prediction in their application. So the service learns from events as reported by each application and predicts next user actions by trying to make sense user behaviors across the boundary of applications. So in particular, we here use a range of well-defined features where each feature is good at capturing certain aspects of user behaviors. For example, in addition to recency I just talked about, we look at how each event is related to the time and the location when the event occurs. We also look at if event occurrences tend to follow certain transition sequences. So we then combine all these features based on how much a target event depends on each of the features. Such a feature dependency varies from event to event. For example, the fact that I go to gym today might more depend on the day of the week instead of how recent it is. So instead of manually specifying these feature dependencies, the system learns these feature dependencies on the fly as it sees user behaviors over time. All right. So this feature analysis were conducted for app launches. As we can see here, at the beginning, so it basically shows the contribution of each feature to the overall event prediction. As we can see here, recency plays an important role at the beginning of the stage usage. As the system observed more and more user behaviors, other features became more important in predicting user behaviors. So our prediction technology has been incorporated in the Android platform. It's in use by millions of users. So in this product feature, it shows full app predictions in the app drawer. It significantly reduce the user effort in searching a target app. In addition to the one-dimensional list we saw, there's a rich space to explore predictive interfaces that can leverage unique aspects of human users and devices. For example, in this ongoing work, we investigate a predictive interface to take into account the user's spatial memory and device constraints watch. In particular, we show top 4 prediction results as 4 enlarged icons at the center of the screen. So their sizes and locations are determined optimally based on their probabilities to occur in their original location in the bezel list. So lastly, I'd like to spend a few minutes talking about cross-device interaction. So far, I have talked about how we can empower mobile interaction for a single device. But our environment is becoming increasingly rich in computing devices that have diverse capabilities and form factors. So to fully leverage this multi-device environment, it is important to combine the unique strengths of each of these devices and to enable interaction capabilities that are actually beyond what each individual device can possibly offer. But it's currently difficult to develop cross-device interactions. Developers need to take care of the varying capabilities of each individual device and distribute output and synthesize input across devices. To address these problems, we intend to develop high-level abstractions and mechanisms for creating cross-device interaction behaviors. As a first step to address these problems, we developed a tool for creating cross-device interaction by scripting. So in this example, we select devices of interest based on their capabilities, and we then use the combine operator, it's a high-level operator, to make multiple devices to behave as one virtual device. With this, the UI is automatically distributed across selected devices. For example, the two buttons are shown on the watch, and the image viewer is on the phone. So this tool has been released as a Google open source project for cross-device programming. I encourage you to try it out. Then last summer, we pushed this work further by enhancing cross-device scripting with interactive illustration. As it types scripts on the left of the UI, the tool immediately visualizes the behavior of the script on the right as a cross-device storyboard. So the storyboard also allows the developers to revise the scripts on the left using direct manipulation. I'm going to show you a quick video about this.
Programming cross-device interactions can be challenging to developers. It can be complex to express interaction flows that span multiple devices. DemoScript is a novel technique that assists developers in programming cross-device interaction. Based on a fundamental understanding of a cross-device UI framework, DemoScript automatically visualizes the scripted behavior by rendering a cross-device storyboard in real time as the developer programs in the editor.
So in addition to providing tools for developers, we're also trying to empower end users, those who directly experience multi-device environments, to be able to program cross-device interaction for their special needs. So this is a very recent work.
Cross-device interaction promises a future where a symphony of devices will collectively enhance users' experience. However, there is a high technical barrier for users to customize how the devices could work together. As a result, users are often restricted to a predefined set of cross-device behaviors, which is unable to anticipate or address their various needs across different scenarios. What if we can let the users conduct the devices and program their own cross-device interaction on the fly? For example, consider Larry, the presenter. Instead of running back and forth between his laptop and the slide projection, Larry can let his phone improvise as a clicker by first demonstrating an action of advancing slides on the presentation app and then a two-finger tap gesture on the phone. Our cross-device input framework interprets Larry's demonstration and maps the phone's gestural input to behave like a clicker. Similarly, Larry can also demonstrate a different cross-device gesture for switching to the previous slide. Larry also wants to go through the entire slide deck in case an audience member wants to refer to a particular slide. To do so, he demonstrates and then uses a one-finger scroll on the phone. Larry can also improvise motion gesture, such as swinging his phone for switching slides. He can also use the phone's touchscreen as a virtual laser pointer. All of these interactions are created and improvised by Larry the user, rather than having to be pre-programmed into the presentation app. Our implementation as a browser extension brings this capability to existing web apps without any access or modification of their source code. As the user clicks the improv icon, it shows a list of available devices and their interactions created by the user. A user can select one to preview which UI elements the interaction is targeted at. The user can also replay the demonstration or adjust the CD gain ratio. Improv also highlights inputs that are too similar to each other. Then the user can mute a conflicting input or simply remove it. Improv focuses on understanding and mapping gestural inputs across devices and applications. At demonstration time, Improv observes a user's demonstrated actions on one device application and learns its input characteristics, whether it's a sequence of discrete actions, or continuous operation of a widget, or some free-form manipulation of digital contents. Next, as the user demonstrates gestures on another device, Improv extracts the most salient features, such as the footprint of a touch event, the spatial relationship between multiple touch points, or the entire touch or motion sequence as a symbolic gesture. The input characteristics inform the style and degree of freedom of the user's intended interactions, which is used to select the appropriate gestural features from another device to be mapped to the original UI. At runtime, Improv dynamically performs gesture recognition and featureization, which in turn generates and dispatches UI actions across devices. Using Improv, web applications without any cross-device capability can now effortlessly support diverse cross-device input. For example, to control this knob widget, a user can improvise one-finger cycling, two-finger turning, one-finger sliding, two-finger sliding, or pinch to zoom. Improv lets users play with and optimize input modalities. To design this t-shirt, instead of using the trackpad to grab tiny manipulation handles, this design appropriates an idle device to improvise some touch-based gestures, so he can bimanually explore the design. It also encourages collaboration. This designer also lets its phone improvise as an input device to work with a colleague on her laptop. Improv also mitigates situational impairment. Before getting into the kitchen, Larry improvises a simple motion gesture with his smartwatch so that he can hands-free pause and play the cooking video. A user can also use Improv to create cross-device macros. Instead of using multiple drop-down lists, this artist can streamline these actions as one single gesture and use it to switch between different painting styles.
All right. So I just want to conclude the talk with a simple slide, just trying to show the type of work I have been working on and the future direction I want to pursue. So from all these projects, one theme that we see repeatedly is that we're trying to combine what the user is good at, the user intelligence or the human intelligence, and what the machine is capable of, the machine intelligence. So we often start with a user-centered design process or learning from user behaviors, and then push the boundary of what the computer system can possibly understand about our actions and behaviors. So this is the direction I'd like to further pursue in the future. Lastly, I want to take the chance to thank the students who have worked on these projects. I only got to show some of our projects. If you want to know more about what we have been working on, please visit my website. Thanks. I can take questions.
Wait, then I have a question. So in the gesture, like in one of the projects you show, the user can do the touch gesture on the touch screen, and then the system can learn the gesture from the demonstration and integrate it into the application. And in that application, you shows, it only tracks the path of the gesture. But nowadays, touchscreen can track more information about the user input, like such as the pressure and the shear force, the angles. I'm just wondering, in a future application or in a future touchscreen application, there are more information from the users, and how would your system expand to include all those kinds of informations?
Yeah, that's a good question. So you're right. It has been just using the touch input for that particular project. So as there are more and more sensor channels, sensor input, it is, in theory, it is possible to incorporate all these sensors into the model. So it's basically, it's a dynamic Bayesian model. It has the transition part and the sensing part. For the sensing part, it can take in many more sensor modalities. But from the inference and the computational perspective, it's certainly feasible to support more sensors. But as you can imagine, from the design perspective, it can be complicated. What gestures could make sense to the user? It's totally complicated. It's something we will need further exploration.
Thank you.
I was wondering, you said you've been doing a lot of work on predictive user interfaces. Has there been much work on predictive user interfaces for individuals with disabilities? I work specifically on design around financial inclusion for illiterate individuals. So the use of mobile phones by illiterate individuals. But I'm just wondering more broadly, for example, blind people, or has there been anything that allows machines to systematically go about predicting what sort of behavior we could expect and then identify it so as to be able to deliver appropriate tools? Yeah,
so I'm not really aware of the work specifically for accessibility purpose, but one main purpose of predictive interfaces is to reduce user input, right? So it will be perfect if the computer doesn't need any input from the user, but it's impossible to do that, most of the time. So I think from that point of view, the predictive user interfaces will definitely benefit people who have a disability. So yeah, I'm not sure if it's answer your question. Just the general purpose of the research area. It will. I'm not aware of. Maybe it's just that I didn't see that work, but yeah, there might be.
Thanks for the talk. I think you hinted at it in one of your earlier slides about, for some of these techniques, you need constant sensing in the background on the mobile device. Can you just talk a bit about that, addressing that challenge, especially if you're going to be transferring this, it sounds like you have, into actual products? Like how closely do the product teams pay attention to that and expect you to resolve or mitigate those challenges as best as possible?
So far it has been just a research prototype, and so we did some experiments with battery consumption, and on that we run the gesture detection code on the DSP chip, because in industry there has been this dual processors, and one processor for processing sensor input, right? So that processor is consuming a little battery, so it can be always up, like in Model X, all these commercial devices. Yeah, so even in iPhone. So we have explored that area in terms of possibilities to integrate this always-on gesture input technique in commercial products. But so far it has been just a research prototype. We haven't really pushed that far to make it into product yet.
Okay, thanks for the great talk. And I think I really like the last slides you mentioned, your future directions, combination of human intelligence and machine intelligence. And as Google as company achieve a lot in the machine intelligence, AlphaGo and lots of AI projects related with the robotics, self-driving cars. So what level of machine intelligence you plan to integrate with your research in the future in general?
So that's really about something I'm going to do. But so from the projects I have presented, I think the machine learning techniques are quite standard, as you can see, like decision tree models and dynamic Bayesian networks. So one direction I'm really excited about, actually, I worked a lot on is to use deep learning to do a lot of work in human-computer interaction. So I'm not able to present some of our ongoing work, but yeah, that's the direction I will see a lot of exciting stuff will come out.
Okay. So yeah, my question is, so you talked about using underlying sensor technology, which is essentially going to be present in multiple devices. You leverage that and provide a uniform framework on top of all these devices. But what do you think about the recognition challenge? As a developer, you could do the fixed mapping of devices, but what about considering a ubiquitous environment? How do you think that will really reflect in real world?
Are you talking about the last project, or which project are you referring to?
View, the
end user programming?
Cross device application development.
Okay, so for the first project, it was more about the cross-device scripting. So it was not much about recognition. So we just assume these recognition components are there or have been developed by others, and we have a few built-in recognition components there. But for the second project, the main problem, research problem we're trying to address there is to be able to map input to the actions on the application side. So that involves some recognition. So the key there was still not on how to recognize the gesture. It was more about how we can map the changes in a gesture to the parameters in the action. Right? It's more about a mapping problem. I'm not sure if I got your question correctly.
I was more concerned about mapping between the device that you select as an input and the device that you're selecting as output, that mapping. Like when device is going, like if I carry my smartphone and define some input there, which has to be reflected on the projector when I'm not here, or if I now move to the different location, will that mapping will be preserved, or how do you think that can be a problem?
Right, so the mappings are actually preserved for specific devices. I mean, if the two devices are paired, the system will remember the mappings you have created for the for the specific pair.
Yeah, thank you.
So please join me in thanking Dr. Lee.
Thank you.